Welcome back to Chem Talks. Today, guys, we are going to continue with our discussion of solutions. And particularly today, we're going to look at one of the properties of solution, and that's solubility. So make sure you take good notes and follow along. Solubility is simply the amount of solute. Remember, that's what's being dissolved, or the smaller quantity. It's the amount of solute that will dissolve in a specific solvent under various conditions. So how much of something is going to dissolve in something else? And there's several factors that influence the amount of solute that can dissolve. This includes the nature of the solute and solvent. We mentioned this a little bit last time when we said not every solute will dissolve in every solvent. We'll go ahead and explain that today. We can also look at how temperature affects solubility. And then finally, we can talk about how pressure affects solubility for gases. Alright, so remember last time we talked about that not all solutes will dissolve in every solvent. It really kind of depends on the chemical characteristics of each of those. So as a rule of thumb that we use to determine whether something's going to be soluble now is this: likes dissolve likes. And what we mean by this is that a solute will dissolve best in a solvent that has similar characteristics, similar chemical characteristics, chemical structure to itself. In regards to, is it a polar or nonpolar? Remember, polar substances don't equally share electrons, nonpolar do. So what we see is that a polar solute dissolves in polar solvents. Okay, example of that be methanol, which is polar, dissolving in water, which is polar. And then the opposite is true. Nonpolar solutes will dissolve in nonpolar solvents. Something like paint, it is nonpolar, will dissolve in turpentine. So the first thing that helps us determine whether something's soluble or not is a solute dissolving in a solvent that's of similarity in polarity. The second factor we will look at is temperature. And we have to look at this in several different phases. First one we'll look at is gases and liquids. And what we see is that as the temperature of the solvent increases, its solubility decreases. It can hold less of the solute or less of the gas. A good example of this is when we talk about trout streams. Okay? So as we increase the temperature, we're increasing the kinetic energy in the system. The molecules start moving faster. As the molecules move faster, they tend to escape, do a phase change. Well, when we look at like rivers and streams, we notice around here that trout like cold water. Why is that? Well, it can hold a lot of dissolved oxygen. As our water decreases in volume, the temperature tends to go up. So late in the summer, our trout aren't really happy because the water temperature is getting a lot higher and we have less oxygen. So as gases and liquids, as temperature goes up, the solubility decreases. Let's look at another example as well. Carbonated sodas. Think about your pop, right? When you take it out of the refrigerator, crack it open, you hear a big release, okay? Well, after sitting around, it warms up, that carbon dioxide continues to gas out and will hold less water than less gas than if it was cold. Solids and liquids. If we look at this chart, generally we can see here's our temperature and here's our solubility. As, for most cases, except for this last one, as our temperature increases, the solubility increases as well. So if we increase the temperature, we are going to increase the solubility. Now let's talk about pressure. Okay, what we see, solubility of solids and liquids are not affected by pressure change, but where we do see them affected is in gases. Okay, so if we look at a gas and a liquid, if we increase the pressure, we increase the solubility. Kind of the opposite of what we just said for temperature and gases, right? If we increase temperature, we decrease the solubility. Well, with a gas, if we increase the pressure, we're going to increase its solubility. Okay. Basically, what we're doing is we're increasing the number of gas molecules entering the liquid by increasing the pressure. Okay. What we're going to talk about with this is what we call Henry's law. Henry's law states the solubility of a gas in a liquid is directly proportional to the pressure of that gas above the liquid. What's this mean? Well, if we decrease the pressure, we're going to decrease the solubility. If we increase the pressure, we increase the solubility. Okay, think about this can of Coke here, or carbonated beverage. Okay, as soon as you open this lid of it, you're decreasing the pressure. You're letting some of the pressure out. Well, what happens? Well, we just decreased the pressure in there, so we're going to decrease the solubility, and what comes out? Well, bubbles. Well, what causes the bubble? It's the CO2 that was put in there earlier. So there's a good example of it. Another good example of Henry's Law is scuba diving. For those of you who aren't aware, scuba actually stands for something, which is self-contained underwater breathing apparatus. No, I'll never test you on that, so don't write it down. But I want to explain some stuff how scuba diving applies to Henry's Law, because it's really important if you ever decide to go scuba diving. Now, you don't need to write this down word for word. Please just get the general idea and be able to explain this. Well, what we know is water is more dense than air. How do we know this? Because our air sits on top of our water, not the other way around. So as we go down in water, we are getting greater pressure changes in water than we do in air. In fact, what we see at the surface of water, we call it 1 atmosphere. As we go down 10 meters, about 30 feet, we increase by 1 atmosphere. You maybe felt that if you've gone in the bottom of a swimming pool. You can feel that pressure building up in your ears, right? Hold your nose, equalize the pressure. So every 10 meters, every 30 feet, we go down, we're basically adding 1 more atmosphere. So how does this relate to scuba diving? Well, as people go down in water, their pressure on their bodies is increasing. So as pressure increases, so does solubility of gas. It means their bodies can absorb more gases. So the deeper a diver descends, the more their tissues are able to absorb gases. Well, think about what we're breathing in. It's basically air, right? Nitrogen and oxygen we're breathing in. Okay. So then as they go up, they decrease that pressure, and the gas that was put in now starts to go out. So the oxygen's not a problem. The oxygen we use up in our cellular process, such as respiration. We go in, we use it, we change it, okay. Nitrogen is inert, meaning it's non-active, kind of like our noble gases are. No, it's not a noble gas. But when it goes in our body, it doesn't really do anything. It just has a tendency to what we call pack into our tissues. It gets pushed into our tissues. So the deeper you go, the longer that you stay down, the more nitrogen that packs in the tissues. The nitrogen itself isn't really a problem. Eventually what it's going to do is get a point of stable equilibrium where it stops packing in. Okay, so that's not a problem. The problem exists is when a diver starts coming back towards the surface. As they go up, they're decreasing the pressure. Well, that nitrogen that was packed in the tissue now starts leaving the tissue. If the diver comes up too fast, or decrease the pressure too fast, the nitrogen comes out in bubbles. Okay, just like we did when we opened a can of soda, same thing, which is a bad thing. Okay, this is what's known as decompression sickness, or the bends. This can have very serious effects. Okay, you can go from simple joint pain or rashes to paralysis, which means you can't move body parts, even can cause death. So be aware of that. It's really important that as they come up, they're coming up slowly. So to avoid this, what they do is that as they come up, divers will make stops at different depths, giving the gas time to what they call degas, or come out of the tissues, not in the gas form rather than a bubble form, and it prevents that decomposition. Okay, they come up slowly enough that the pressure is released, so it avoids all that pain. Okay, the last thing we're going to talk about today then is the rate of dissolving. How quickly can a solute dissolve in a solvent? Okay, so it depends on 3 different factors. First of all, what's the surface area of the solute? Secondary, is there any stirring or agitation going on? And the third one is going to be the temperature. So let's quickly look at all 3 of these. All right, let's look at the first of the 3, and that's surface area. Surface area just refers to how much area is on the outside of the thing. If we increase the surface area, we're going to increase the rate of dissolving. Think about it. Where do things start dissolving? Do they start dissolving from the inside or the outside? Well, when we're talking about solutes, they dissolve from the outside. So if we increase the surface area, that's going to be more of an area for them to dissolve from. It dissolves in a faster rate. Okay, the second one is stirring. If we increase the stirring, we're going to increase the rate of dissolving. Why is that? Well, if we start stirring it, it's going to keep it from clumping together. If it clumps together, we're going to reduce our surface area. So by stirring or agitating it, we're going to once again increase the surface area, give us a faster rate of dissolve. Let's talk about our last one, and that's temperature. as we increase the temperature, we increase the rate of dissolving. What's going on here? Well, remember, think back to when we talked about energy. As we increase the temperature, our particles are moving faster, and that causes them to come into contact with the solute more often and increasing the rate of dissolving. This happened to me at lunch today. I took my Nalgene of water out of the refrigerator and I poured it in my favorite drink mix, put it up, and started to shake it. Why? Well, shaking, as we talked about last time, should increase it. But since it was so cold that it actually kind of clumped together, even though I was shaking it, and it slowed down to dissolve. It took probably 2, 3, 4 minutes to actually get all my drink mix to dissolve in there. The last thing we're going to talk about is saturated solutions. Think about when you were a kid. Your mom let you make Kool-Aid, right? You got your pitcher of water. You open your Kool-Aid in there, and your red direction said 1 cup of sugar. So you put 1 cup of sugar and stirred. Well, you thought, well, if 1 cup's good, 2 cups must be even better. So you put another cup in and stirred. Maybe 3 is even better. Eventually, you got to a point where no matter how much you stirred, you couldn't get in any more of the sugar dissolved. And that's what we call a saturated solution. A saturated solution is a solution which contains as much solute as can possibly dissolve under the existing conditions, being temperature and pressure. If we change temperature and pressure, we can get it. But under the current conditions, it's kind of maxed out. That's why no matter how much you stirred, you couldn't get any more of that sugar to go in. So any more solute, any more sugar you put in will not be dissolved. It just kind of clumps up on the bottom there. Now, we can make what's called a supersaturated solution. These are pretty cool. It's a solution that contains a greater amount of solute than is needed to form a saturated solution. So if we've momentarily altered these conditions of temperature and pressure, one or the other, and got more solute to go in, and then we kind of let it sit there and get back to its normal. Now, it's very unstable. It wants to come out of that supersaturated solution pretty quick. Okay, so it doesn't maintain on the saturated state for very long. If you dropped a couple more crystals of sugar in, you would see all of a sudden all this sugar would magically come out of the solution. I'll show you a video on this in class next time. So here's an example. Unsaturated, as we put our sugar crystals in, they dissolve. When we get saturated, rather than dissolving, they start piling up. And the supersaturated, we can actually get the formation of crystals because we've heated it up and then let it cool down, and we get this really cool supersaturated. Google it or YouTube it for supersaturated solutions. I'll show you some in class, but it's pretty cool. All right, guys, thanks for sticking with me today. Once again, if you have any questions, please stop by and see me before class. Until next time, guys, take care. Here's bonus material for you. If these 3 bears got in a fight, which ones would disappear? The white ones, because they're both polar bears. As we learned, likes dissolve likes.